All right, guys, so we're finally starting chapter 5, Better Late Than Never. And lesson 5.1 is all about curve sketching. So it's going to give you a function, and it wants you to use calculus to help sketch that function and what it looks like. So there's a little recipe that is given to you here in the textbook of the things that you want to use, the things that you want to find and keep in mind when you're making this, sketching this curve. So the first thing that you want to think about is looking at the original function. What's the domain of the function? Is there anything that we're square rooting or something that's going to make the denominator 0 in the original function that's going to restrict our domain? Okay, maybe a natural log function or anything that might restrict what x's are possible. Okay, number 2 is you simplify the original function. So whatever f of x is, you're going to try to factor out and cancel out anything on the top and the bottom that you can. Doing that helps you find holes. So number 3 is to find the vertical asymptotes and the holes. Remember, the holes come from when you're simplifying f of x. If something cancels on the top and the bottom, that can imply that there's a hole there. If something doesn't cancel, but it does cause an issue, like turning the bottom into 0 or square rooting a negative, then that would give you a vertical asymptote. Step 4 is to find the x and the y intercepts. Sometimes this is very necessary if it wants a more accurate curve. Sometimes you're just estimating the curve and you don't actually find these points. Today we will on most of these. We're going to find the x and the y intercept. So to find the x intercept, you set y equal to 0. To find the y intercept, you set x equal to 0. Finding end behavior. Remember, you look at the function and consider, this is where you look at top heavy, bottom heavy, or if they're equally heavy. And so you look at the coefficients of the top and the bottom to tell you what's happening as you go all the way to the right and all the way to the left. Is your function getting really big, really small? Is it approaching a asymptote at some value? Increasing, decreasing intervals is what we kind of practiced a lot in chapter 4. We're increasing and decreasing. We use our derivative, and we use that as well to find our local extremes, like relative maximums, relative minimums. You find the derivative, figure out what makes it equal 0, check the left and the right, all that fun stuff. And same thing with step 7, except for you're going to use the second derivative to check concavity and points of inflection. So step 8, use all that information and graph. So example number 1, we're just going to do 3 examples here in the video. These are the same 3 examples that we're going to go over in class in case you weren't here. If you need to fast forward, if stuff is making sense and it's easy and you're sick of listening to me talk, I'm going to try not to go too fast. I'd rather you fast forward than try to slow me down and make things sound really goofy. So example number 1 is a rational function, 2x cubed divided by x squared plus 1. These problems are really nice because it also gave you f prime and f double prime. So you're not having to find those. They're already given to you. So first thing we want is there any domain restrictions? Is there anything that's going to make my denominator 0? And since x is getting squared and becoming positive, it's never going to be 0 on the bottom. There's no square roots to worry about. So my domain is all real numbers. I don't need to worry about restricting that anywhere. Vertical asymptotes. When I look at 2x cubed and x squared plus 1, I can't simplify this function. I can't reduce or factor out or factor and cancel things. So I'm not going to have any vertical asymptotes. And same with holes. Because nothing factors out and I don't have anything being removed, there's also no holes on this first one. x-intercepts. Now remember, to find the x-intercept, I set y equal to 0. And to find the y-intercept, I set x equal to 0. So if y is equal to 0, then that means 0 equals this. And I multiply the bottom over, that goes away. And I've got 2 times x cubed. What makes that equal 0 is just x equaling 0. So my x-intercept is 0, 0. My y-intercept, if I plug in 0, I get a 0 on top right here, which makes my overall value 0. So my x and my y-intercept are 0, 0, which we should have known, right? After finding the x-intercept being 0, 0, obviously the y-intercept has to be the same thing. And behavior. So what happens is I go really far to the right in this function. So what I want to look at is what happens as x approaches infinity. So x is going to get really, really, really big. And when I look at this function, I have an x cubed on top, but only an x squared on the bottom. So this is top heavy, which means I'm going to end up with something really big on top and something really small on the bottom, which means that as I go to the right, as I go to infinity, my function, as I go to the right, my function is going to approach infinity. It's going to get really, really big. As I go to the left, it's still top heavy, but I'm plugging in negative infinity. So right here where I cube my infinity, I end up with a negative number on top. So I still go to infinity, but since the top is negative and the bottom is positive, as I go to the left, I'm going to approach negative infinity. So it's going to look like this on the right, and it's going to look like that as we go to the left. All right. Relative maximum. Here's where we look at, this is all of our chapter 4 stuff. We're going to look at our critical numbers. So I'm going to use f prime. Where did my pen go? I'm going to use f prime, and I want to know what makes that equal 0. What are my critical numbers? And when I do that, my critical number, I only have 1. Nothing on the bottom is going to make it 0 because I plug in something, it becomes positive. I add 1, it's still positive. I square it, it's still positive. So no number on the bottom can become 0. On the top, though, if x is 0, if that right there is a 0, then I multiply the parenthesis by 0 and I end up with a 0. So I can get a 0 on the top. So I have one critical number, x equals 0. And so now I make my cool little chart for f prime. I'm wanting to know what's happening to the left and right of 0. So I pick a number to the left, -1. I pick a number to the right, 1. And I plug those into the derivative. So when I plug in a 1 right here, when this is a 1 and this is a 1 and this is a 1, my bottom is positive, right? I end up with a positive number on the bottom. I don't care what it is. It's just positive. On the top, I get a positive times 2, which is positive, times x squared plus 3, which is positive. So I get a positive over a positive, which means to the right of 0, my function is increasing. Now, if I look at the left of 0, if I look at -1, when I plug in a -1, it gets squared on the bottom and becomes a +1. So my bottom is a positive. And if I plug in a -1 on the top, it gets squared, becomes positive. It gets squared, becomes positive. So I end up with a positive on the top as well. So to the left of 0, my function is increasing. And then at 0, it stops. And then to the right of 0, it's increasing again. So that means I don't have a maximum or a minimum because my function is always increasing. Except for at 0, technically it's not increasing or decreasing. So I guess my function is never decreasing. All right. So points of inflection. So I want to know where is my function. This is going to help me know when it's concave up and concave down. So I've got to consider f double prime, which again, it's really nice that it gave that to me. And I'm looking for possible points of inflection. So what could make f double prime equal 0? Nothing on the bottom. It doesn't matter what I plug into the bottom. The bottom is always going to be a value. It's never going to be 0. So I want to know on the top, if I have negative 4x times x squared minus 3, what's going to make that equal 0? Well, if I put x equals 0 in right there, the whole thing becomes 0. So one of my possible points of inflection is 0 itself. But this could also equal 0. And so if x squared minus 3 is the factor that equals 0, then x squared equals 3, which means x equals the positive and negative square root of 3. I hate it when it does that to us because it's not a nice number, right? So x could be 0, x could be square root of 3, and x could be the negative square root of 3. So when I do my little sign chart here, I've got to consider, I better make this a bigger sign chart, right? I've got to consider 0. I've got to consider square root 3 and negative root 3. But I don't want to look at those numbers. I want to look at numbers a little bit bigger and smaller. So bigger than 0 but smaller than root 3 is something like the number 1. Smaller than 0 would be negative 1. Bigger than root 3 would be the number 2. Smaller than negative root 3 would be the number negative 2. So these numbers I'm going to plug into f double prime. And again, all I'm interested in is the sign. I'm not interested in the number I get. I'm just interested in what value or what sign I get. Is it a positive or a negative number? So when I look at f double prime, it doesn't matter what I plug in the bottom. The bottom's always going to be a positive value. So really, all I need to look at is what happens when I plug a number in the top. So let's start with negative 2. If I plug in a negative 2 on the top, I end up with a positive 8 multiplied by negative 2 squared is 4. 4 minus 3 is a positive number. So I get a positive times a positive, which stays a positive. So that means before negative square root of 3, my function is concave up. Now, if I plug in a negative 1 times negative 4 is a positive number, but negative 1 squared is positive 1 minus 3 gives me a negative number. So on top, I get a positive times a negative, which means my top number is going to be a negative. So in between negative root 3 and 0, my function is concave down. Now let's plug in a positive 1. The bottom's going to be positive. This is going to be a negative number. This is going to be a negative number. So that's going, a negative times a negative gives me a positive. So I'm concave up again. And then plug in positive 2. This gives me a negative number. This gives me a positive number. So a negative times a positive gives me a negative. So it's concave down. So I switch from concave up to concave down at x equals negative root 3. And I switch from concave down to concave up at x equals 0. And I switch from concave up to concave down at x equals root 3. So all of those are the x values for my points of inflection. It wants to know where those are on the graph. So I actually have to plug all of these into my original function to get my y values. I've already done 0 because I did that up here. So one of my points of inflection is 0, 0. When I plug in negative square root 3, you are welcome to plug that in. You're going to end up with what? Square root negative square root 3 cubed is going to become a 3 times a negative square root 3. So that's going to become a, let's see, what are we plugging in? Negative square root 3. So on top, I'm going to end up with what? 6 root 3, negative 6 root 3. I think it's negative 6 root 3. On the bottom, negative square root of 3 cubed, or squared, is just going to be positive 3. And then I'm going to add 1, and I'm going to end up with a 4 on the bottom. And things are going to cancel and simplify. So instead of negative 6 over 4, I end up with negative 3 over 2. Yikes, that was fun. Hope we can do that again. Oh, we get to, because now I have to plug in square root 3, and I'm pretty sure I'm just going to end up with positive root 3 over 2. So I have and if I'm wrong, you can tell me in class how bad I am at math. Now that I have all this information, I want to graph, all right? I want to take this information and use it to help me draw this function. So I start with my points. 0, 0 is a point. I also know negative root 3, which is smaller than negative 2, right? And then negative 3 root 3 over 2 is going to be down here further than negative 2, so we'll just put it right about here somewhere. And then positive root 3, again, is going to take me over, not to 2 yet. And then I'm going to go up past 2, so it's going to be up here somewhere. It looks like those are the only points that I know. So now I know that my function is always increasing, meaning it's always going like this, right? Because when I found my critical numbers and used my derivative, I saw that my function is always going up. But it's not always concave up or concave down. It switches. So when I look at this information, before I hit this point, negative root 3, I'm concave up. So my function is something like this. But then when I hit root 3, I change to concave down until I get to 0, which looks maybe something like that. And then I switch to concave up again. Whoops, I don't erase. That's not what I wanted. I get concave up until I get to positive root 3, and then I get concave down again. Now, end behavior tells me what to do with the ends of my graph. As I go to the right, we said that I approach infinity. So my graph is going to keep going up. As I go to the left, I'm going to approach negative infinity. So my graph is going to keep going down. So my graph looks something like this. Okay. On the AP test, they're pretty, as long as you've got the major points and concavity is obvious, they're pretty flexible with your function. They're not going to say, actually, the graph was steeper in between those points like this, and so we're going to take points away because you didn't make your graph steep enough. They're just looking for those main characteristics. The points are the points, and it's concave up when it's supposed to be, and it approaches infinity when it's supposed to, and so on. All right, next example. Another rational function, f of x equals 3x minus 2 divided by x squared minus 2x plus 1. All right, this one, domain restrictions. Is there anything that's going to make the bottom become 0? I think there is, because this actually factors to become x minus 1 times x minus 1, and it doesn't cancel. But there is a number that I can't put on the bottom. X, oops, where did my pen go? X cannot equal 1 in my original function, because that would make my denominator 0, and that's we can't do that. So X can be anything else, it just can't be 1. Now, even though x squared minus 2x plus 1 factored, it doesn't simplify, nothing cancels, so there are no wholes. which leaves x minus 1 left on the bottom. So that means that at x equals 1, I'm going to have a vertical asymptote. And not only that, I know a little bit more. If you go back to secondary math 3, because x minus 1 actually shows up twice, we call that even. And it's going to have an even asymptote, which means if this was my asymptote, because there's two x minus 1s, if the left side goes up, the right side's also going to go up, okay? If there were three x minus 1s, like if there was another x minus 1 here, if it was cubed, then I would still have the same asymptote. But if one side went up, the other side would go, whoops, that's not what I wanted. The other side would go down. So they would be opposite. Whoa, I am doing all kinds of stuff I don't want to do. See what happens when I try to talk more than I should? So there is a vertical asymptote at x equals 1, and we know that it goes up and up, or it goes down and down as it approaches that asymptote, because there's two of them. X-intercepts. So what happens when y is 0? And for the y-intercept, what happens when x is 0? I'm going to check y first, the y-intercept, because plugging x in to be 0 is really easy to do. On the bottom, I end up with 1. On the top, I end up with negative 2. So that means my y-intercept is just negative 2. Now my x-intercept, I have to set 3x minus 2 over x minus 1 squared equal to 0. So when I multiply that over, it goes away. So 3x minus 2 equals 0. So 3x equals 2. So x equals 2/3. So there are my points on the graph. And in fact, I can put this information on right now as I go. I have an asymptote right here. Right? Actually, you know what? I'm going to do that in blue so we can see it a little bit better. I have an asymptote right here. I have a point, 0, negative 2. So I've got a point right there, and then I have another point, 2/3, 0. So I've got another point right about there. Maybe I should make those points smaller. I don't know. Okay, so there's a couple points on my graph, and I know there's an asymptote. Cool. End behavior. So let's look at what happens to my function as I approach infinity and negative infinity. All right. So if on the top I have 3x minus 2, on the bottom I had x squared, which means this is a bottom heavy function, right? The bottom is going to get a lot bigger than the top, which means if I have something small on top, something big on bottom, then I'm going to approach 0. So as I go to the right, I'm going to approach 0, which means as I go to the left, I'm also going to approach 0. It doesn't matter if it's a negative or a positive. Either way, the bottom gets really big, the top gets really small, and I'm going to approach 0. So I also know that I have this asymptote right. Oh, we did our asymptote in blue, huh? So I have another asymptote right here and right here. I guess, I'm sorry, not an asymptote, but as I'm approaching infinity, I'm going to approach that line, 0. So it's kind of like an asymptote, even though I actually touch it in other places. Okay, relative maximum. So now to find my relative maximum, I've got to consider the derivative. So here's my derivative right here, and I want to look at my critical numbers. So what is going to make my derivative equal to 0? The bottom, if I were to plug in x equals 1, that would give me an error, right? But I can't use 1. Remember how 1's not in my domain? So normally, one of your critical numbers could be not negative 1. It could be 1, but we're not allowed to use 1, so I don't even have to consider 1. So I just need to look at what makes the top, 3x minus 2, equal to 0, right? Or not 3x minus 2. I used the wrong equation. We're looking at the derivative. Negative 3x plus 1 equal to 0. So when I minus 1, divide by negative 3, x equals 1/3. So that's my critical number. So I want to look at what's happening to the left and the right of 1/3. So if this is 1/3, let's look at 0. And we can't look at 1 because we can't plug in 1. So we've got to use... And actually, you know what? We have a vertical asymptote at 1. So we need to pick something in between 1/3 and 1. So let's do 1/2 because that's bigger than 1/3 but smaller than 1. And then we need to look at what's happening on the other side of the asymptote. So let's plug in the number 2. Because remember, an asymptote can change if my function is increasing or decreasing, just like a critical number can, right? All right, so if I plug in 0 to my derivative, remember this is f prime that we're using. If I plug in 0, I get a negative on the bottom, and on the top, I get a positive. So from 0 to 1/3, my function is decreasing. My function's going down. Then I hit the 1/3 point, right? So let's look at what's happening at 1/2. If I plug in a half, on the bottom, a half minus 1 is a negative, so I still have a negative on the bottom. And on the top, negative 3 times a half is negative 1.5, plus 1 is a negative, so I end up with a negative over a negative, which means my function is increasing in that in between 1/3 and my asymptote. And then from when I plug in a 2, 2 minus 1 is a positive, cubed is a positive. 2 on the top is negative 6 plus 1, which gives me a negative. So again, after I'm decreasing. So my function does change direction. I'm going down until I get to 1/3. And then at 1/3, I start going up, which means I have a relative minimum at that 1/3 value. So if I plug in 1/3 to my original function, take this 1/3, plug it in here, you end up with what on top? 1 minus 2, so that's negative 1. On the bottom, you end up with 1/9 minus 2/3 plus 1, which is 1/9 minus 6/3 plus 9/3, which is 1 minus 6 is negative 5 plus 9 is 4. Not 4/4. Come on, Mr. Reed. 4/3. So that's negative 1 over 4/3. Nope, those aren't thirds. God, I'm trying to go too fast here, and I'm doing things. This is 6/9 and that's 9/9. There we go. That sounds better. So this is 4/9, and when I flip that over, it becomes 9/4. So this value is actually negative 9/4, which is cool because I have another point. At 1/3, I go down a little bit more than 2. I go down to negative 9/4. So we'll put a point right there. All right, points of inflection. We're almost there. This is like a 45-minute video to do a couple problems. I know, I apologize, but they're just long. So possible points of inflection. I need to use f double prime. What would make f double prime 0? If I look at f double prime, that's this one right here. Again, it gives it to me. The only thing that would make the bottom 0 is a 1, and I can't use that. I can't use a 1. So the top would become 0 if x was 0. So when I do my little chart, I'm going to check f double prime, and I'm going to check to the right of 0. But when I do that, again, we're going to have to check something. We've got our asymptote we've got to consider. So let's pick something like a half, and then let's pick something like 2, and let's pick something like negative 1. We can keep this pretty simple. So when I plug in a -1, I end up with, remember I'm plugging this into F double prime. So I end up with a negative on top, and I end up with a -2 to the 4th, a positive on the bottom. So that means I'm concave down until I get to 0. Once I get to 0, let's see what happens. If I plug in a half, then my top is positive. Where's my pen? And on the bottom, 1/2 minus 1, it's still positive. So actually from 0 to my asymptote, I'm concave up. My concavity changes. Cool. So that means 0 is going to be a point of inflection, 0 comma something. And then let's see what's happening on the other side of the asymptote. When I plug in 2, I get positive on top, positive on bottom, so I'm also concave up. All right, so my point 0, we already found that one, right? Yeah, we already found that point. It's 0, -2. So I don't get a new point on my graph, but I get a point that I already know, and it tells me that to the left of that point, so this is the point right here, to the left of that point, I'm concave down. And I'm decreasing according to my derivative. So if I'm concave down and I'm decreasing, then my function is going something like this. Whoops, that was terrible. My function is going like this. I know it's not going to cross. I've got this asymptote right here. So I know I'm not going to actually reach 0, but I'm going to approach it. Now, in between 0 and this little dot right here, this little section right there, I'm concave up. I'm concave up in between there, and I'm increasing according to my derivative. So if I'm concave up and increasing, no, I'm not increasing till I get to 1/3. So never mind. I'm concave up, and I'm actually still decreasing, which makes sense because now instead of going down, I start getting bigger, which is really hard to draw. But see, if you look really close, it's concave up, right? And then once I get to that point, I'm still concave up, but now my derivative tells me that I'm increasing. So concave up and I'm increasing means I'm going to go up like this through this point, and I know that I'm not going to hit that asymptote. So it's going to look something like that. As far as the other side, two things could be happening. Theoretically, we know one of them's not happening, but theoretically my function could either be doing this or this. But I have a couple of hints which one is correct. First of all, my second derivative told me that after the asymptote, I'm concave up, which makes this not an option. But I also know that my asymptote is an even asymptote, which means that on both sides of my asymptote, they should be going the same direction. So because this arrow that I just erased is going up, because I'm going up right here, I'm also going up right here. So this would be the correct line, and it's going to approach but not cross that 0 line down there. Okay, so that means that line doesn't exist. So my function looks something like that messy disaster. And again, as long as your concavity is correct and your points are correct, the detail of exactly what the slope is and how steep doesn't really matter. All right. Okay, let's do one more, if you can last that long. So number 3, a radical function. F of x equals x on top, square root of x squared plus 2 on the bottom. Whatever I plug in on the bottom is going to become positive and then get added to 2. So I don't have to worry about the denominator becoming a negative. I also don't have to worry about the denominator ever becoming 0, because whatever number I get, it's a positive and I'm adding 2 to it. So I'm never going to end up at 0 either. Vertical asymptotes. Well, nothing simplifies. Nothing makes the bottom 0, so there is no vertical asymptote. And since nothing simplifies and cancels out, there are also no holes in this function. Hopefully this is a nice one. Let's hope it keeps going like this. X-intercepts. So what happens when y is 0? And for the y-intercept, what happens when x is 0? Let's do x being 0 first. If 0 is on top, well, it doesn't matter what's happening on the bottom. My answer is 0. And if I cross at 0, 0, that means that I also cross at 0, 0. So my x and my y-intercepts are the same. Okay. End behavior. So let's plug in infinity and negative infinity. So as I go to the right, I'm going to change x to infinity and x squared to infinity squared. I'm going to end up with this square root and this square, technically you can't cancel them out because of that +2. But when I am going to infinity, that x squared becomes so huge that +2 doesn't matter. So even though I've got an x squared with something else in there, it's kind of like my square root and my x squared cancel each other out. So I basically end up with infinity over infinity, which means that all I have to look at is what's in front of the x squared. And in this case, I'm going to end up with just 1. I have a 1 on the top and a 1 on the bottom. So as I go to the right, I'm going to approach 1. Now, as I go to the left, something a little bit different happens. I still end up with, these two still cancel, and I end up with negative infinity on the top. But on the bottom, I took negative infinity and I squared it. And that turned it into a positive number. And then I square rooted it, and it's still a positive number. So on the bottom, I end up with positive infinity. So instead of having the same coefficient, this is like having -1 over +1, which means that as I go to the left, I'm going to actually approach -1. So this is kind of a cool picture, because as I go to the right, this is going to become my asymptote. And as I go to the left, it's going to be down here. Okay, relative max and minimum. So let's look at f prime. The top is always positive. The denominator, it doesn't matter what I plug in on the bottom. It's never going to become 0. And in fact, it's always going to be a positive number. And so I end up with a positive over a positive all of the time. So my function is always increasing. It's going up everywhere. So that means I'm not going to have a relative maximum, and I'm not going to have a relative minimum, because it just keeps going up. Now the point of inflection, we better double check, because this may not work out the same way as the relative max and min. The bottom is still never going to become 0. So all I have to worry about is the top, -6x becoming 0. And that actually can happen when x is equal to 0. So I do have a possible point of inflection, x equals 0. So I'm going to do my little sign chart, 0, +1, -1, and this is for f double prime. So if I plug in a +1, I end up with a negative on the top and a positive on the bottom, which means I'm concave down. If I plug in a -1, a -1 times a -6 is a positive number. I still have a positive on the bottom. So this section, it's concave up. So that does mean here is a point of inflection. At 0, we already know what it is, at 0, 0. That is a point of inflection. So this point right here is my x-intercept, it is my y-intercept, and it's also a point of inflection. So now we're ready to graph. To the left of that point, I'm concave up. but my function is increasing. So that means as I approach 0, my function is going up, right? So it looks something like that. And I could be more dramatic probably. If I wanted to, I could make it look a little bit more concave up. But then once I hit 0, my point of inflection changes my concavity, and now I'm concave down, but I'm still going up. So my function simply looks like that one. It never crosses 1 to the right, and it doesn't cross -1 to the left. It approaches them, and it stays the same concavity. It just never actually crosses those lines. So, all right, time for you to try this. Assignment 5.1, go ahead and do all of the problems. These steps are going to help you a lot. These 1 through 8, finding the domain, reducing F, asymptotes, holes, X and Y intercepts, and behavior. You've done most of this in secondary math 3, but increasing, decreasing concavity might be new, and this is a way easier way to find it than anything you would have done in secondary math 3. So go ahead, do all the homework problems. Please don't try to do number 5 before you do number 4. Okay, number 5 looks like it might be messy, but if you do number 4 first, number 5 is actually a 30-second problem. So make sure you do number 4 before you try to do number 5. And we'll see you in class to answer any questions.